Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. In the last class, we have started the chapter on mechanical separation technique. Today, we will continue in that. So, mechanical separation technique deals with the separation of different phases of the material by the use of some mechanical force, and it has a difference with the separation based on the size that we did in screening, or with the membrane separation where the selected permeation takes place normally. So, in that mechanical separation we have discussed in the last class, and today we will continue with the topic first, that is filtration. Filtration has enormous use in food processing industry, many methods. For example, filtration of juice, different kind of slurry, and although this kind of filtration, when we use a slurry and we want to separate it from the solid and the liquid part. So, based on the requirement, sometime the slurry is important, sometime the liquid which is after filtering we are getting, that is important, or sometime both are important. So, filtration may be defined as the separation of solid from liquid by passing through a permeable medium. Okay. So, we can see how the arrangement look like. This is a frame is there or support is there for filter medium, and there is a filter medium, this one is a filter medium. Okay. And as the slurry comes over the filter medium, the liquid will filtrate through the filter medium, and the slurry will be deposited on the on top of the filter medium. And as time will continue, the deposition of slurry will deposition of cake will increase, and because of that the pressure differential will also change. So, initially since the there was no deposition, so rate of filtration was very high, and as the deposition increases, okay, so the rate will further lower. So, therefore, with time we need to remove the filter cake that is being deposited on the filter medium. The suspension of solid and the liquid to be filtered is known as the slurry, and the filter medium used to retain the solid, that is in the form of cake. So, the valuable stream for the filter may be the fluid or the solid or both, as I said, and the driving force across the filter medium and the cake is basically responsible for the filtration process to occur. So, next we will see that rate of filtration, which is actually the most important parameter for us who wants to know the process or want to design any process. So, the rate of filtration should be maintained properly. The fluid passes through the filter medium, which offers resistance to its passage under the influence of a force, which is the pressure differential across the filter. So, to cause the rate of filtration, we need driving force divided by resistance. So, if the driving force increases, so rate of filtration will increase, and if the resistance increases, rate of filtration will decrease. Resistance arises from the filter cloth or mesh or filter bed, and to this the added resistance occur because of the deposition of the cake. Filter cake resistance is obtained by multiplying the specific resistance of the filter cake, that is the resistance per unit thickness, because as the deposition of cake increases, so it offers resistance in a higher scale from the initial condition. So, if we know the specific cake resistance, we can analyze better that how it going to affect the rate of filtration. Now, coming to the theory of filtration, that is what is the mechanism behind filtration. So, here we will assume that with start of the filtration, if we continue it for a time, let us say t second, then the deposition of cake will occur and the length of that deposition, let us say L meter. Okay. So, in that we have taken a section, a very small section of having length dl in the cake across the area A of the filter medium. Okay. So, the slurry is coming and it is flowing in a cross flow situation as we have taken. So, deposition of slurry will be more in this case. So, in that deposition which has occurred in time t second, we have taken a small section dl across the area A in meter square, and also we want to interested in the calculation of the linear velocity of the filtrate, which is here v meter per second. Okay, linear velocity. Now, with that we will start calculating the case for pressure drop across the filter cake. Now, for that we will start from the approach that we normally take when we try to analyze any pipe flow. So, when we want to analyze pipe flow for any fluid in laminar condition, okay, and in that we want to have a distance pressure drop across a distance delta L. Okay. So, then we use Hagen-Poiseuille's equation for laminar flow in case of a pipe, and there we try to make a relation between the pressure drop delta P, which is P1 minus P2, okay, pressure drop with the diameter of the pipe and the velocity of the fluid and also the viscosity of the fluid. So, similarly here what we will do is we try to first equate this with that particular case, that is delta P across the length L, that is equal to 32 mu v by d square, which is Hagen-Poiseuille's law. So, the basis is first this law. Then what we assume that if instead of flowing a fluid through the whole pipe, if we fill it with the particle of similar dimension, okay, and pack it completely. If we pack this completely and we assume that there is a we assume that the pores between them will frame like a channel, linear channel, and through that we want to flow the fluid, and also we want to measure that if the laminar flow prevails, then what will be the pressure drop. So, this kind of analysis you will read in transport phenomena when you try to analyze the porous media flow, etc. So, from that concept we will try to relate this pressure drop for the filter cake. So, now if we will relate it by this equation, that is V will be equal to dV, very small amount of liquid which has been filtered in time dt, divided by the cross sectional area A. So, this will give us the idea of linear velocity. Okay. So, then what we will do is now the velocity through a packed bed, that has been given by the Karman-Cogini equation. As I mentioned that when you deal the porous media flow, you will get to know this equation, Karman-Cogini equation and Black-Cogini equation. So, there are different equation, Argon equation, which relates the pressure drop across the length of L in a porous media and the velocity. Also this equations has been developed for laminar flow as well as for the turbulent flow. Here we will use the equation for the laminar flow, and the relation is such that delta Pc divided by L, we consider the cake as a packed bed. Okay. So, delta Pc divided by L, that is the pressure drop across the bed, okay, or cake. L is the length that has been deposited, K1 into mu into V 1 minus epsilon square H0 square by epsilon cube. So, these parameters are: K1 is a constant whose value generally taken as 4.17 for random particles of definite size and shape. Mu is the viscosity of the filtrate in Pascal second. V is the linear velocity based on filter area in meter per second that we have just calculated, that is dV by dt upon A. Then we have epsilon, which is void fraction or porosity of the cake. Okay. So, this is epsilon, void fraction or porosity of the cake. Then L, we know the thickness of the cake in meter, S0 is the specific surface area of particle in meter square of the particle area per meter cube. So, specific surface area, that means meter square of the surface area per meter cube of volume of the solid particle, okay, meter square area per meter cube of the volume of solid particle. Delta Pc is the pressure drop in the cake in Newton per meter square or Pascal. So, this is the relation. Now, we try to relate this with other equation that we can derive from the particular case where the figure we have drawn, that the deposition of the cake and the filtrate. So, relating those equation we will try to get some idea of the pressure drop across the cake. So, how we can develop that? First, we have seen that what will be the flow of fluid through that. Okay. That means about the filtrate that has been passed through. Now, we try to establish a material balance to get some idea then how the deposition of cake has occurred. Okay. So, for that a material balance through the filter cake we have developed, that is, you know, L is the length of the cake. Okay. So, if I draw the figure here, this is the filter medium, okay, and in that L is the length of that deposition. This area is A, okay, this is the whole area of the cake, okay, and there is a porosity, that is epsilon. So, this L into A giving the total volume into 1 minus epsilon, okay. So, this is the void fraction. So, epsilon is the void through which the liquid will pass, okay. So, 1 minus epsilon, that means the cake, the fraction of the cake. So, that will be equal to the deposition V, the volume V that has been passed through plus the volume that has been, you know, that has been there in the cake. So, in the cake volume of the fluid is epsilon into L into A, okay. And here if I write now that Cs and here rho p, where rho p is the density of the cake that has been deposited and Cs is the kg of the solid per meter cube of the filtrate. So, then we will get this material balance. Okay. So, the length of L into cross sectional area, that is the volume, 1 minus porosity, that is giving the cake which is there, into density, that is the mass of deposition of the cake, will be equal to the volume that has been passed through, because this volume also contain Cs kg per meter cube of the solid material. So, this volume plus the volume which is retained in the cake in the pore. So, epsilon into La plus V into Cs. So, this is the idea that we are getting from the mass balance. Now, using this equation and the previous equation where we have got the Black-Kochner equation relating the pressure drop with the length and other parameter. So, with this equation we are getting this final equation, which is dV by dt divided by A, that is the velocity. So, velocity will be equal to minus delta Pc, that is the pressure drop across this cake, divided by K1 into 1 minus epsilon into S0 square by rho p into epsilon cube into mu into Cs V by A. So, what we have done is that we have replaced this L from here, and from the previous equation, the Black-Kochner equation, we have replaced L, and then we have tried to express this in terms of V, which is the linear velocity. So, then we are getting this equation. So, all the parameter K1, epsilon, S0, mu, that we have expressed, Cs, area A, rho p. Okay. Now, this equation can be further represented as delta Pc, which is the driving force, divided by resistance. So, resistance is alpha into mu Cs V by A. Okay. So, if you look into this two parameter, first one is this one and second one is this one. So, K1 specifically for the bed of particle or the size of the particle if they are uniform. So, based on that cake property only. Porosity also of the property for cake only. Rho p is the density of the cake. S0 is the specific surface area of the particle per unit volume. So, all this represent the property of the cake specifically. Therefore, we have combiningly expressed this in terms of alpha and call it specific cake resistance. Okay. Multiplied with mu, that is the property of the filtrate that is going out, into Cs, that is kg of solid per meter cube of the filtrate, into volume V by A. So, this is how we can express this as driving force by resistance. Okay. So, therefore, we have taken all this factor as alpha, and alpha can be defined as this way: K1 1 minus epsilon A0 square by rho p into epsilon cube, this one. So, dV by dt, that is if from here I want to write that dV by dt can be written as A multiplied with delta P, this is pressure drop. So, this is reducing in the that way we have kept minus sign, by R, which is the resistance. Now, for the filter medium resistance, what we can write? We have seen now that how filter cake resistance can be formed, but definitely some resistance will be provided by the filter medium as well. So, for that what we will do is we use a factor Rm. So, similar manner that way we did we calculated for the filter cake, that is V is equal to dV by dt divided by A, that is equal to minus delta Pc by alpha into mu Cs V by A. Similarly, we have calculated for the filter medium resistance as dV by dt by A, Similarly, because that linear velocity we assume that will be fixed from the cake also and as well as for the filter medium as well. So, that will be instead of delta Pc now delta Pf, that is because of the filter medium divided by mu into Rm. So, mu is the viscosity and Rm is the resistance of the filter medium to filtrate the flow in per meter. So, this is the unit of this Rm, and this includes the resistance to flow of the piping leads to and from the filter and the filter medium resistance. Delta Pf is the total pressure drop across it. Now, since the resistance of the cake and the filter medium are in series, because the slurry is coming into first the deposition of the cake is there, then there is the filter medium is there, okay, and then the clear liquid is going out. So, they are in series. So, we can club those two pressure drop delta Pc and delta Pf to find the total pressure drop across it. So, therefore, we can write dV by dt by A, which is nothing but linear velocity, that is equal to minus delta P divided by, we have taken mu as common, here also mu was there. So, alpha Cs V by A plus Rm. So, delta P is equal to delta Pc plus delta Pf. Now, filter cake compressibility. So, all the cake formation that is deposited on the surface on the above of that medium and depositing in the form of a cake. So, that may be sometime compressible as well. Also, most of the cases we take it as incompressible, but we can find the factor of compressibility. So, what is that? With some filter cake, the specific cake resistance, that is alpha we have taken, varies with the pressure drop across it. So, this is because the cake becomes denser under the higher pressure, and so provides fewer and smaller passage for flow. That means, the pressure drop and porosity has a relation. As the packing is more, pressure is more, so the porosity will be changing, and the effect is spoken as the compressibility of the cake, because when the pores is small, that means it has the compressibility is there. So, it is usually possible to express the voidage Ez at a depth of Z. So, at a depth of Z in the cake, what will be the if we take a dz section, so what will be the porosity? So, that will be a function of the pressure drop from the top face where the slurry is coming in to the Z depth, what is the pressure at the Z depth. So, based on that this porosity will be varying. So, therefore, we can define alpha will be equal to alpha 0 into minus delta P to the power S. So, this alpha, what we have got this relation is alpha equal to alpha 0 into minus delta P to the power S. Okay. So, here we can write this alpha equal to alpha 0 into minus delta P to the power S, this we have got. Now, also if we look into the expression of the alpha that we have related with the constant K1, with the porosity, with the density of the cake. So, all the parameters were there. So, here alpha is the specific cake resistance under the pressure P, delta P is the pressure drop across the filter, alpha 0 is the specific resistance of the cake under a pressure drop of 1 atmosphere, okay, and S is the constant for the material called the compressibility. So, here when the S relates the compressibility, that means S can be changed for a different kind of a pressure. So, the value of S can be changed if it is a compressible cake. So, from the equation that we have developed for the specific cake resistance, we have seen that alpha has a relation, that is alpha is a function of porosity, S0 that is specific surface area of the particle per unit volume of the particle, and also the delta P, okay, because if delta P changes, porosity changes, and for that alpha is also changed. So, this is the factor. So, constant pressure experiment at various pressure drop develops the relation between alpha and delta P. So, if you want to try to get an idea then how delta P is going to affect the specific cake resistance, then what we need to do, at different constant pressure we need to perform the filtration operation, and then we need to see that what is the value of this resistance coming. So, constant pressure experiment at various pressure drop, and thereby we can develop a relation between alpha and delta P. So, if alpha is coming independent of minus delta P, that is pressure drop, the sludge is incompressible, and usually alpha increases with delta P. Okay, specific cake resistance increases with increase in delta P. Since most of the cake are somewhat compressible, an empirical equation often we use, that is alpha equal to alpha 0 dash into minus delta P to the power S. The compressibility constant S is 0 for incompressible sludge or cake, and the constant S usually falls between 0.1 to 0.8 for the incompressible cakes. Now, coming to the factors affecting the rate of filtration. So, the rate of filtration is proportional to the pressure difference across both the filter medium and the filter cake. So, the pressure drop can be achieved in a number of ways. First one is gravity, where a pressure difference could be obtained by maintaining a head of slurry above the filter medium and depend on the density of the slurry. Another method is by vacuum. The pressure below the filter medium may be reduced below atmospheric pressure by connecting the filtrate receiver to a vacuum pump. So, thereby we can create the pressure drop. And third thing is centrifugal force. The gravitational force could be replaced by centrifugal force in particle separation. So, all three forces are used in different kind of filtration mechanism to cause the pressure drop. And another thing, that is the rate of the area of filtering surface, that has an effect on rate of filtration, and the another important parameter is the viscosity of the filtrate. Okay. So, normal assumption is that with increase in the viscosity of the filtrate, the resistance of the flow will also increase. Okay. And increase in the viscosity of the filtrate will increase the resistance of flow. Obviously, because if it is a thick viscous liquid, it will not flow so easily. So, that the rate of filtration is inversely proportional to the viscosity of the fluid. So, that is why rate of filtration is inversely proportional. So, if viscosity increasing, rate will decrease. Now, what could be the solution for this kind of problem? So, then we can do two things. One is we can increase the temperature. Okay. So, by raising the temperature of the liquid, the rate of filtration may be increased. Now, in a practical case, we should keep in mind that if we raise the temperature, whether any heat sensitive compound will degrade or it will it can handle the filter medium that we are using. So, looking into all that, we can apply either point 1. Second is dilution is another alternative. So, in the case where we can't apply temperature, we can go for dilution of the slurry. So, in that it will have the effect in the rate of filtration. Another point is the resistance of the filter cake. So, definitely resistance will going to affect the rate, and the resistance of the filter medium and initial layers of cake. So, this will also have effect on the factors. Okay. So, we will stop here and we will continue in the next class. Thank you.